For finite sets, like this one, we define the cardinality of the set as the number of elements in the set. So the cardinality of this set of colors is 4. So it's easy to see when two finite sets have the same cardinality. My sets T and S have the same cardinality because they both have 4 elements. For infinite sets, it's not quite so obvious when two sets have the same size or cardinality. For example, consider the set, I'll call it J, of even integers, and the set Z of integers. Well, J and Z are both infinite sets, but J is contained in Z. So should we say that J and Z are both the same size, or are they different sizes? What about the set of integers and the set of real numbers? This video will start to answer these questions by giving a precise definition of cardinality for all sets, including infinite sets. But before we go there, let's think a little bit more about what we really mean when we say that this finite set has cardinality 4. When we count up the elements, we're putting them in a one-to-one correspondence, or a bijection, with the numbers 1, 2, 3, 4. We could also put the elements of T in a one-to-one correspondence with the numbers 1, 2, 3, 4. But we could also see that the set S and the set T have the same size without actually referring to any numbers, simply by making a direct one-to-one correspondence between the colors in S and the letters in T. This is similar to how you might decide that they're the same number of children at a party as there are party hats, simply by giving each child a party hat. If there's a perfect bijection, a perfect one-to-one correspondence between children and party hats, no children left over, no party hats left over, and no doubling up, then we know that we have exactly the same number of children as we do party hats without actually ever doing any counting. This idea of a one-to-one correspondence is a fundamental idea when we try to define the cardinality of infinite sets. So we say that two sets, A and B, have the same cardinality if there exists a bijection between A and B. A bijection is another word for a one-to-one correspondence. In other words, there exists a map F from A to B that is one-to-one and onto. When A and B have the same cardinality, we write the cardinality of A equals the cardinality of B. We say that the cardinality of a set A is less than or equal to the cardinality of B if there exists an injection from A to B, in other words, a one-to-one function that is not necessarily onto. When the cardinality of A is less than or equal to the cardinality of B, we write cardinality of A less than or equal to cardinality of B, and we write the cardinality of A is strictly less than B if the cardinality of A is less than or equal to B and the cardinality of A is not equal to the cardinality of B. That is, there exists an injection from A to B, but there does not exist a bijection from A to B. A set is called countable if it is either finite or has the cardinality of the set of positive integers. We'll call the set of positive integers n. The word countable makes sense here because if the set's finite, we can certainly count it. But if it's in a bijection with the set of positive integers, it might take us forever, but the bijection with the positive integers gives us a way of counting the elements of the set, right? We just point to the elements of the set and say the numbers as we go through the bijection. A set is called countably infinite if it is countable but not finite, i.e. it can be put in bijection with the positive integers. And when a set is countably infinite, we say that its cardinality is aleph naught. That kind of looks like an N, but it's actually a Hebrew letter, aleph, with a subscript of 0. A set is called uncountable if it is not countable. So it is not finite, and it cannot be put in a bijection with the positive integers. Now, at this point, you may be asking, well, what infinite sets are countably infinite, and which ones, if any, are uncountable? Let's talk about that next. So I have 6 pairs of sets here. And for each pair of sets, see if the set in the A column and the set in the B column have the same cardinality or a different cardinality. That is, can you find a bijection between the two sets, or is no bijection possible? You may not be able to answer all of these questions right away, but think about it for a minute and then come back to the video. The set of positive odd integers and the set of positive even integers are the same cardinality. An easy way to put them in bijection with each other is to take an odd integer, x, and send it to x plus 1. This function, I'll call it f, is 1 to 1 because if f of x1 equals f of x2, that means that x1 plus 1 equals x2 plus 1, which means that x1 equals x2. F is onto because if y is in the set of positive and even integers, then y minus 1 is in the set of positive odd integers, right? Because the smallest positive even integer would be 2, and 2 minus 1 is 1, is still a positive odd integer. And f of y minus 1 will equal y, so therefore f is onto. So we have a bijection between these two sets. They have the same cardinality. To me, that makes a lot of sense. Things get a little weirder from here, though. The set of positive integers and the set of positive even integers also have the same cardinality, even though this set B is strictly contained in this set A. To build a bijection, we can define the map G that takes x to 2x. I'll let you work out the details that this map G is indeed a bijection, and therefore these two sets have the same cardinality. Now, you may be worrying, what if we defined a map H instead from the positive even integer to the positive integers just by H of, say, H of y goes to y. This map H is 1 to 1, but not onto. So you might be worrying, doesn't this show that our set B is strictly less than the set A? Because we have a 1 to 1 function that's not onto? But no, it doesn't. It simply shows that B's cardinality is less than or equal to the cardinality of A, this function. It doesn't show that it's strictly less than. To show that it's strictly less than, you have to not only have an injection, but show that there's no possible bijection. Even though this particular map's not a bijection, that doesn't mean there's no possible bijection. So it doesn't mean that B is strictly less than the cardinality of A. In fact, there is a bijection. And this is the bijection right here. Of course, we could make it go the other direction too, since it's a bijection. And so therefore, these two sets actually do have the same cardinality. What about the set of positive integers together with 0 and the set of positive integers? Again, we could create an injection from here to here that's not a bijection because it's not onto, just by inclusion. But that doesn't mean that the sets have different cardinalities. Because if we can find some other map that's actually a bijection, they'll have the same cardinality. And in fact, such a bijection does exist. I'll call it H, and I'll just take, say, z, positive integer or 0, to z plus 1. Again, I'll let you check that this map is actually 1 to 1 and onto. Things get even weirder from here. Turns out the set of positive integers and the set of all integers also have the same cardinality. Even though the positive integers is in some sense infinite only in one direction, and all integers is in some sense infinite in two directions. Here's an example of a bijection. We take 1 and send it to 0, 2 and send it to -1, 3 and send it to 1, 4 and send it to -2, 5 to 2, 6 to -3, 7 to 3, and so on, alternating between negative and positive numbers. Although it's possible to put a somewhat complicated formula to this, like we did to the previous bijections, it's not necessary in order to show that the bijection exists and is one-to-one and onto. It turns out that number 5, the positive integers and the positive fractions, are also the same cardinality, but the positive fraction and the positive real numbers are not the same cardinality. There's some really cool proofs of these surprising facts that we'll get to in class or possibly in another video. So, which of these sets on this page are countably infinite sets? Recall that countably infinite means the set can be put in bijection with a set of positive integers. From the second example, we see that the positive even integers are countably infinite because they can be put in bijection with the positive integers. Of course, the positive integers themselves, they're the OG countably infinite set. The positive odd integers, they can be put in bijection with the positive even integers, which can be put in bijection with positive integers. So therefore, the positive odd integers are countably infinite. The positive integers and 0 are countably infinite because of this bijection. The set of all integers is countably infinite, and the set of positive fractions is countably infinite. And the only set on this page that's not countably infinite is the set of positive real numbers. Since it can't be put in bijection with the positive fractions, it can't be put in bijection with the positive integers either, because if it could be put in bijection here, then we'd have a bijection with the positive fractions. I'm using here the transitivity of bijections, right? If A is in bijection with B and B is in bijection with C, then A is in bijection with C, simply by composing the two bijections. In this video, we defined two sets to have the same cardinality if and only if there exists a bijection from A to B. We also saw that there are a lot of sets that can be put in bijection with the positive integers and are therefore called countably infinite. We stated, but didn't prove, that there are some infinite sets that are not countably infinite. In particular, the set of positive real numbers is uncountable. Stay tuned for a proof of that later.